Welcome everyone to our Friday's Lockheed Martin Weldon Robotics Center seminar. It's my pleasure to introduce our speaker today, Dr. Xuesu Xiao, soon to be Professor Xuesu Xiao. So he is currently a research affiliate at the University of Texas at Austin, working closely with Texas Robotics. And he's also a roboticist with the Everyday Robot Project at X, which is part of Alphabet, which also owns Google. It's complicated, but they've been sort of working on very, very cool robots for domestic service use, and we'll be talking a little bit about that. He obtained his PhD in computer science in 2019 from Texas at Texas A&M, and his master's from CMU.
Yes.
Right? Dr. Xiao is an expert in machine learning for navigation. I think he has some very hands-on experience deploying machine learning algorithms in the context of navigation, and when you shouldn't apply machine learning for navigation. His interests are in continual learning for robots that are deployed in the field and that improve over time, over long periods of time. So I'm very excited to hear his thoughts. So without further ado, please take it away.
Yeah, all right. Thanks for the introduction. So hi everyone. So I'm Xuesu Xiao, roboticist on the Everyday Robot Project. I'm also affiliated with UT Austin. I'll be studying assistant professor at George Mason in the fall semester. So I'm very excited to share to you all about our recent work on deployable robots that learn. So first of all, I want some definition first. So by deployable, I mean robots that are able to move to places in the real world in order to execute certain tasks. And also through learning from other robots, learning from their own experiences, learning from humans, or learning from other robots. These robots need to adapt to a variety of different tasks and different scenarios during real-world deployment. So ideally, we would like to deploy, for example, Iron Man to save our lives during a plane crash. We would like to deploy Baymax to provide us with both mental and physical health care. We would love to have robots like R2-D2 or TARS being deployed 24/7 around us to provide us with any assistance anytime we need it. But unfortunately, these deployable robots only exist in science fictions. To achieve this level of deployability, we still have a very long way to go. But we also have currently deployable robots in our lives. For example, we have deployed robots in, for example, factories and also in warehouses for decades. We have deployed robots to vacuum cleaning our homes, and we have seen robot shows by hundreds of drones. We have also deployed robots in modern surgery and the safety and defense sector. However, compared to the ideally deployable robots shown in the last slide, what makes these robots to be currently deployable in the real world? If you think about it, most of them are either being deployed in highly controlled workspaces or being deployed to execute one single pre-programmed task. But these robots never learn anything to deal with the changes in the real world, or no matter how many times they repeat the same pre-programmed task, they will never improve their navigation, they will never improve their deployment performance in the future or adapt to any new tasks in real-world deployment. These two assumptions are required for current robots to be autonomously deployed in the field. That is why for uncontrolled environment and also for novel tasks, today's robots must seek help from highly skilled human operators during field deployment, because we as humans, like surgeons or like bomb squads, can be trained and learn to master new things in every new deployment, but not the robots. So today's robots' the lack of ability to learn causes this very extensive dependency on humans. As a roboticist, my dream is to bridge the gap between the last two slides, the ideal versus the current, by developing highly capable and intelligent mobile robots that are robustly deployable in the real world with minimal human supervision. So most of those deployment problems actually comes from the field. So our research will adopt a field methodology, working with physical robots, working in the real world, and also with real robot end users, such as first responders, firefighters, and agency stakeholders. So our expertise is evenly grounded in both classical motion planning to create capable locomotors on land, in air, and at sea, and also machine learning. So to equip those robots with intelligence, especially the intelligence required to make them fully autonomously deployable, hopefully with as minimal human supervision as possible. During my PhD back at Texas A&M with Robbie Murphy, we have done extensive work in the intersection of field robotics and motion planning, especially under the context of disaster robotics, where we use robots to replace human rescuers in disaster responses. So these are just some of our recent efforts to make disaster robotics autonomous. So for example, the modular snake robot shown on the upper left shows, so those robots are teleoperated by robotics experts and also local responders in the Mexico City earthquake. So one of our recent work utilized overhead security cameras and a locomotive reduction technique to autonomously drive those hyper-redundant snake robots in those collapsed buildings to search for victims. And in the middle, we show the Emily robot. So it's a jet-powered flotation device being deployed in Greece refugee crisis. So the Greece Coast Guard have to manually drive Emily from the shoreline, having trouble with depth perception and being very inefficient. So we teamed Emily up with an unmanned surface vehicle, unmanned area vehicle, and UAV. So with the visual post-stabilization method we developed and the visual navigation approach, so Emily is able to autonomously navigate to drowning victims in the water with visual assistance from the air. And on the right, we show the Fukushima and Daiichi nuclear disaster decommissioning. So where multiple human operators have to cautiously and also slowly drive one packbot into the contaminated power plant to do the decommission work. So, but the problem with this is we also require a secondary packbot just to follow the first one, providing the first operating crew, the human operating crew, with necessary situational awareness to do the decommissioning. So imagine the increased manual labor and the communication burden between the two groups of operators. So in our PhD thesis, we replaced the secondary packbot alongside with its human operating crew with an autonomous tethered aerial visual system, which flies around with a tether in those unstructured confining environments, and also reasons about viewpoint equality based on affordance theories, and also reasons about motion risk using a risk awareness framework. However, if we use classical motion planning techniques to make disaster robotics autonomous, but these approaches do not give the robot the ability to learn, a very natural ability all the current human operators already have. So beyond disaster robotics, there's also many other different application fields. These are just some examples. So in order to be deployable in all these different application fields, there's one common key capability necessary, which is navigation, the ability of a robot to move from one point to another reliably and safely. Some people may think that navigation is already a solved problem, and indeed, we have been studying navigation for decades. And we have, for example, the very robust implementation of the ROS move-based navigation stack available for many different mobile robots. But I would like to argue that navigation is not a solved problem, is far away from being solved for actually autonomously deployable robots in the field. The very fact that most robots being deployed in the field are piloted by skilled human operators means current autonomous navigation capability still lags behind, especially when we deploy in challenging or even adversarial real-world deployments. So usually we require multiple human operators to drive one single robot. And in addition to that, there's always the safety officer on site overseeing the scene to make sure nothing is going wrong during real-world deployment. So even if when we deploy autonomous navigation, as you can see by the example video on the right, in this the robot has trouble navigating through this very narrow and curving corridor, and we will need robotics expert knowledge on site before every new deployment to make sure that the autonomous system can work very well. Truly intelligent robots should never repeat these mistakes in the field, but actually learn from them, learn from their experiences, and learn from humans and also learn from other robots. So just like their current human operators would do. So learning for navigation, you may ask, have roboticists already tried to do that? So this is a simplified version of a figure we just published in a survey paper we just published in Autonomous Robots on using machine learning for motion planning and control for mobile robot navigation. I know it still looks quite complicated, but let me walk you through it. So at the bottom of this figure, it is a classical navigation pipeline, horizontally from left to right. So we have the global planning subsystem, which takes in the global goal and produces a local goal in the middle. And we also have the local planning subsystem, which takes the local goal from the global planner and produces raw motor commands to move the robot in the real world. At the top, we show the scope of learning of each of the papers we surveyed. So the width of each of these colored blocks represent what are the classical components at the bottom that the learning approaches encompasses. So we didn't show the specific 74 papers, I remember, in the survey, but we only list the numbers of papers that belong to each of those blocks. So the darker the block is, the more papers are targeting at the components covered by this block at the bottom. So the take-home message of this figure is a vast majority of works approach navigation using machine learning in an end-to-end manner. A small amount of work learns the global planning subsystem, some work learning the local planning subsystems, and also on the navigation component level, some work learning the global representation, learning the global planner's parameters, learning local representation, and also learning local planner's parameters. So with all these different learning approaches for navigation, the next question you may ask is, how well do they work? What are their navigation performance during real-world deployments? So we also compared their navigation performance against their classical motion planners, classical navigation counterparts. So the x-axis is decreased learning scope in 3 course categories, so end-to-end learning, learning subsystem, learning components, as you have seen in the previous slide. And we also organize all these works in a different dimension. So the y-axis is increased navigation performance compared to their classical counterparts, including underperformed classical, duplicated classical, and improved classical. So better performance towards up. So there is a very significant concentration of works at the lower left corner. So these works are end-to-end learning and can at most duplicate what is already achievable by their classical counterparts. And 11 of them are even worse. We also, you can also see a rough correlation between decreased learning scope and increased performance along this diagonal line. So the more focused the learning approach is, the better the overall navigation system performance it can achieve. So this is what the survey tells us. If we use learning at the right place, it may be able to improve overall navigation performance of our deployable robots. So in today's talk, I'm going to talk about 3 different approaches or 3 different locations in the classical navigation system to improve navigation during real-world field deployment. The first one is called Adaptive Planner Parameter Learning, or APPLE. So APPLE answers the question, can robots learn from non-expert users? So non-expert is the keyword here during actual field deployment. So in our classical navigation pipeline, APPLE targets at the parameter level of local planners. So the motivation of APPLE is, so deploying an autonomous navigation system in a new environment is not as straightforward as it may seem. So for example, if you have just deployed your robots in this outdoor environment and then the next deployment is in this indoor space, directly deploying the same autonomous navigation system may not always work out of the box. So, and also, even within one existing navigation environment, so if there's one very difficult spot in the middle, like the very narrow doorway there, if the robot struggles at the first time, may get stuck or maybe collide with the door, it's more than likely that the second time when it comes back here, it will repeat the same mistake over and over. So as roboticists, we all know that we just need to spend some time fine-tune the navigation system to make sure the parameters of the system are correct for this new environment or for this difficult environment. But for someone who is not familiar with the underlying navigation system, this process is not trivial. But our inspiration for APPLE is even non-expert humans can do the navigation task effortlessly. So this is Bo, one of our PhD students in the lab. He is able to just grab an Xbox controller, teleoperated robot to navigate through this very complex obstacle course, even on his very first try. So the central question we would like to ask in APPLE is, can we squeeze more robust performance out of our existing navigation systems using very limited human interaction with non-expert users and also machine learning? So to be specific, we are not interested in learning or inventing a brand new end-to-end navigation system, but augmenting existing systems to make them better deployable. So for example, this widely used ROS move-based navigation stack, and APPLE is agnostic to the underlying navigation system and can treat it as a black box. So in this way, so all the benefits of these classical navigation systems can be inherited, such as safety and explainability, so which are extremely important when we are deploying physical robots in the real world. And APPLE, the machine learning piece on top, can give the classical systems the flexibility and adaptivity of machine learning. So I'm going to talk about one particular work in detail that is called Adaptive Planner Parameter Learning from Demonstration. So in APPLE-D, we propose to use behavior cloning to tune any navigation stack. So to be specific, we describe a navigation system as a function G, which takes in sensor data X and outputs motor commands U. G is also parameterized by a list of tuning parameters. For example, maximum speed, sampling rate, and also optimization coefficients, etc. So usually there's a very long list of these parameters to be tuned. And these parameters are crucial in determining the navigation system's performance in a new deployment scenario. So we treat this as a classic use behavior cloning to treat this as a supervised learning problem. Basically, we are seeking theta star here, the optimal parameter set, to minimize the difference between our demonstrated action UI and the output of our function G, parameterized by theta. So the rough procedure of APPLE-D is, during actual field deployment, the non-expert user just needs to collect a demonstration of the desired navigation behavior. And then we can use any black box optimization technique to find that optimum parameter theta star. However, there's one problem here, which we call context problem. If we're only using one single theta star for the new scenario. For example, in a scenario like this with like qualitatively different regions, so humans may also drive very differently. So therefore, one single theta star may not be sufficient, and we need to learn separate theta stars for all these different regions, which we call different contexts. So in addition to use black box optimization and on the collective demonstration, we also perform an extra automatic demonstration segmentation using Bayesian change point detection techniques to segment this whole demonstration into different pieces. Then, instead of learning one single set of parameters for all the demonstration, we learn one single set of parameters per context. Then we also train a neural net-based context predictor to identify where the robot is based on the perception input X. So the context is K. So during field deployment, we use this learned piece. So B5 will predict the context K based on sensor data X. And then this mapping M is a static mapping to map from the K to the appropriate set of parameters theta star, because theta K star to be used by the underlying planner. So in our experiments, we use a ClearPath Jackal with a Velodyne LiDAR with human demonstration collected in this complex obstacle course. So in this video, the top half shows the vanilla move-based performance with the DWA planner with its default planners from ClearPath Robotics, which is the manufacturer of the robot. And the bottom half shows the learned behavior through AppleD. You can see in the first curved context, the default parameter suffers by stopping and recomputing the samples over and over, while AppleD can drive through straight. In the second obstacle course, AppleD also drives faster. In this third curving corridor, sampling rate is increased while maximum speed is decreased. So AppleD learns to very confidently and very slowly navigate through, while the default parameters need to stop and recompute many times and even requires human intervention. In the last open space context, AppleD increases the maximum speed and drives straight towards the goal location, just as the human has demonstrated before. So this shows AppleD works pretty well for Jackal's DWA local planner. But you may ask, how about other robots maybe running different planners? So this is a different robot called BWI bot. It runs the E-band elastic band planner as its local planner instead of Jackal's DWA planner. So the default E-band planner parameters will cause this very oscillatory behavior shown on the left, even if it's a straight hallway. And the roboticists in our lab have tried to manually tune the parameters of E-band planner and come up with the result in the middle, shown as tuned. And AppleD can completely eliminate this oscillatory behavior and result in a perfectly straight line shown in green on the right. So given a full teleoperated demonstration from non-expert users, so we can fine-tune the navigation system's parameters to adapt to different deployment scenarios. But what if a full teleoperated demonstration from joystick commands are not available from the user? Can we also utilize other different interaction modalities with the user to improve navigation in the field? So under the same adaptive planner parameter learning or Apple paradigm, we have developed a suite of different Apple methods. For example, so robots do not behave suboptimally everywhere during field deployment. Some places it performs pretty well. So humans, non-expert humans, only need to intervene only when necessary. So this motivates our Apple I work, adaptive planner parameter learning for interventions. So robots are only need, the human, the non-expert human only need to take control of the robot at these specific points, showing red and yellow. And we also augment our context predictor with a confidence measure so that for the green parts, which is unseen or unintervened, it can generalize very well. And some users may not be able to take full control of a moving robot with a joystick. They don't feel comfortable, but they still know if a robot is doing a good job or maybe a bad job. So therefore, we also develop a third Apple approach, adaptive planning and parameter learning from evaluative feedback. So the Apple E agent can make decisions, learn to make decisions just from a very simple scalar or even binary feedback from the user, like a thumbs up or thumbs down. And utilizing the power of reinforcement learning in simulation, we have developed our Apple R method. So Apple R method learns a parameter policy in this benchmark for autonomous navigation or BARN dataset that we created. So BARN composed of 300 navigation environments randomly generated by cellular automata. And the Apple R agent can learn to make planning decisions in such a way that the robot may even take suboptimal actions at one state in order to perform better into the future. So taking one step back, I would like to, we also formalize all these 4 individual methods under one single unified adaptive planning parameter learning Apple paradigm. So there's a comparison between the classical like end-to-end learning paradigm for navigation versus Apple's parameter learning paradigm. So in the classical end-to-end learning paradigm, we learn a motion policy pi_m, which directly interfaces with the physical word w, shown at the bottom, and using a state x and also a reward function. So the action space of pi_m is the raw action commands to be executed on the robot, such as v and omega, linear and angular velocities, to be used by the robot to directly influence the real world w. While on the right, we show this Apple's parameter learning paradigm. So instead of the motion policy pi_m in end-to-end learning, we learn a parameter policy pi_p, which does not directly interfaces with the physical word w shown at the bottom, but a meta environment we call E, which is composed of both the classical motion planar G and the physical word W. And through a meta state shown on the left, this meta state S, which subsumes the robot state X and also a reward function. So the parameter policy can take actions not in the raw action space as A in the left, but the new action space for parameter policy is the parameters to be used by the underlying classical motion planar G. So by dynamically updating the motion planar G's parameters during field deployment, it can adapt to different new scenarios in the real world W. So we also combine all these four methods together under the same Apple umbrella. So to form a cycle of learning scheme, so robots can iteratively and cyclically learn to improve into the future. So by cycle of learning, I mean like one particular deployment with one single non-expert human interaction should not only be targeted at the current deployment alone, but any future deployments like in a cyclic fashion throughout the entire robot's lifetime. And also, one single robot's lifetime is not our ultimate goal. So in the future work, so more and more robots are deployed in the field together with different human users. So these robots should also learn from not only themselves, not only from their own human user, but also other humans and also other robots. So these robots from the same robot manufacturer already have a very natural infrastructure to share experiences, to transfer knowledge, and to crowdsource interactions with different users. And within that robot manufacturer, computation is not limited by the onboard computation limitations during field deployment. So the cycle of learning scheme can be used to iteratively and cyclically improve the entire fleet's navigation performance in the field. So this wraps up our first Apple approach. So Apple can enable robots to learn from even non-expert users, non-roboticists during actual field deployment. So the second part of the talk is going to be about learning inverse kinodynamics, or LIKD, to enable accurate, high-speed, and off-road navigation. So it answers the question, can robots learn, instead of from non-expert users, can it learn from its own self-supervised in-situ interactions with the deployment environment? So in the classical navigation pipeline, instead of learning the parameter of the local planner using human interactions, so LIKD learns an inverse kinodynamics model to adapt continuous motions at the end without any humans in the loop, with self-supervised interactions with the environment. So three things combined together will make navigation even more challenging. If you want to drive accurately, if you also want to do that at very high speed, and if you want to do that on off-road unstructured terrain. So if you want to do a very fast lap time using your vehicle in this complex off-road track, so the adversarial effect of all these three things will be magnified as you increase your navigation speed. Our inspiration here is the robot can actually learn a kinodynamic model through its own self-supervised robot environment interactions during deployment. In our case, we are learning from vehicle-terrain interaction to enable off-road navigation. So formally speaking, we would like to navigate a mobile robot to track a reference trajectory during deployment as quickly and also as accurately as possible. And remember, you need to do this on unstructured off-road terrain. So this is basically to minimize cost function with two terms, the total traversal time t, and also the accuracy of trajectory execution. So remember, you need to minimize this cost term on all unstructured off-road terrain whose features are not known a priori before your deployment. So putting this under classical controls paradigm, so we have our controller here, so which is usually in the form of an inverse kinodynamics model. So it takes the desired trajectory as input and outputs the vehicle controls U. Through a forward kinodynamics function, which is our real world, the robot state will change in its own state space X. So, but the problem with doing this on off-road terrain at very high speed is there's also this unknown world state W, which has a big influence on the forward kinodynamics and caused by all these different types of terrains. And usually this W is unknown, and it's very difficult to analytically model before the deployment. So in our approach, we utilize onboard perceptions, onboard sensors, learning a function of the world state x, w, and the robot state x, using this observation function g. It will give us our onboard observation y. And then we learn an all-terrain model, which takes y as input and can be used by the controller, by our inverse kinodynamics model. So to be specific, we are trying to learn to approximate the true underlying model F inverse shown on the bottom there. So our approximation model is parameterized by theta, F theta dagger. So the key difference between this true underlying model and the approximation model is, while the true model takes W, unknown W as input, our model instead swap W with the tangible Y, the onboard observation as input. So during real-world deployment, robots can collect vehicle-terrain interactions using its own self-supervised experiences. For example, it can collect vehicle controls, U, robot state X, observations Y, and also the actual outcome of rolling out the real-world forward kinodynamics delta X. This will give us our training set. So then, in order to learn our inverse kinodynamics model, we basically regress on the following laws. So we pretend the actual outcomes, what we observed during data collection, were actually desired. And then we are seeking this theta star. This theta star here is not a hyperparameter of a like local planner as we talked about in Apple, but this is the parameters of the model, like neural nets weights and biases. So we are trying to minimize the difference between U, which is our observed vehicle control during data collection, and the output of our approximation function F theta dagger, taking delta X, X, and Y as input. So to implement our model, we did that on a 1/10 autonomous vehicle called UT Automata. So we, for the onboard observation, we take the IMU readings from an inertia sensor onboard that vehicle. And for this Ackermann steering vehicle, so the control input is basically linear velocity and the steering curvature. So we instantiate our learned model using a neural network model shown on the right. So taking the last 106-dimensional IMU readings as input, we concatenate them and feed them into our learned embedding system. So the embedding system will give us a 2-dimensional embedding Y, and then we concatenate that Y with the desired change rate of state of the vehicle, delta X on the bottom, which is given by some high-level global planner, and we feed that into our learned IKD model. It will give us the correct motions to be executed on the robot. So in this video, we show the learned performance of the LIKD model on this complex off-road track. So you can see there's very different terrains like trees, leaves, grass, mud, cement, and also like twigs and stuff. And more importantly, there's a combination of them. So it's very difficult to model them. So we don't treat them as separate terrain classes, but we learn an all-terrain model to cover them all. As you can see, using our model, despite very extensive disturbances from the real world, from the terrain, the robot can still drive at a very high speed, but still maintain very high accuracy. We also compare it against a default model, which is manually designed by humans, and is mostly good for like homogeneous terrain and also for low speed. As you can see, our green model, the learned model, is more successful than the default model because the default model fails many times, stuck at some point, or even collide with the track walls. We also test our generalizability shown on the bottom. So this is the unseen indoor track, which is not seen by the model. So it can also navigate much better than our default model when we increase the speed. So we test 10 different speeds on this off-road track shown here with 3 models. The baseline you have seen before. The blue is a ablation study we designed. So the training using the same set of training data, but removing the dependency on the onboard observation Y. Green is our model. As you can see, at lower speed, the green trajectory is always the closest to the black reference trajectory, showing black, while the red is the furthest away. And with increasing speed, the red trajectory starts to scatter around and being very inconsistent. And such a trend is less obvious for the blue and also for the green trajectory. And each of those little dots at each of the turns denotes how many failure cases the corresponding model experiences. Failure means either getting stuck or maybe colliding with the obstacles. So the smaller size of all these green dots at each of those turns, meaning so our learned IKD model is more successful, is more accurate at high speeds. So we also observed the same trend in this unseen indoor wooden floor terrain. So the green trajectory is closer to the black reference trajectory, while our the baseline is further away. So we list some numbers here: failure rate per turn, per speed, shown on the left part, and also per turn, shown on the right part. So on the top is the seen terrain, the training environment, and the bottom half is the unseen terrain. You can see at most of those cases, the green bar is shorter than both the red and the blue bar, meaning our model achieves much fewer failure cases compared to the baseline and the ablation study. But there's one thing I would like to point out here in this graph, which is this turn 8 here. This turn 8, so the green bar is actually higher than both the red and the blue, meaning our model fails more frequently than blue and red. This is because if you look at the graph shown on the right, so this is the turn 8, T8 here. So at turn 8, the vehicle is traversing from a low grip grass area onto a high grip cement area. So our learned IKD model knows, based on the IMU readings on the grass, the robot needs to oversteer in order to compensate for the lack of friction between the vehicle wheels and the terrain. But because of high speed and also actuation latency, when the robot just entered from a low grip grass to the high grip cement area, the vehicle is still oversteering. So the oversteer command plus the suddenly increased friction between the wheels and the cement will cause the robot to turn too much and collide with its inside wall, the white panel here at turn 8. So this is a problem. So we have a very recent follow-up. It's under review right now. So to deal with this problem. So in this visual inertia inverse Kinodynamics or VIIKD work, the robot, in addition to inertia information, it also extract a vision patches in front of the robot and then learn a visual representation space to anticipate upcoming kinodynamic changes during high-speed maneuvers. So in addition to the IMU readings, the vision can help for it to anticipate future changes in terms of kinodynamics. So it can deal with those problems we encountered at turn 8 in the last slide. So this wraps up our second approach. So LIKD can empower robots to learn without any humans in the loop, but learn from its own self-supervised in-situ interactions with the deployment environments. So the third work I'm going to talk about is called Safe Learning from Hallucination for Highly Constrained Navigation Environments. So it answers the question, also without any humans in the loop, can robots learn from their own self-supervised experience from previous deployment in order to benefit future deployment experiences? So in our classical navigation pipeline, LFH has the widest learning scope. It learns the entire local planner without humans in the loop again. So the motivation of LFH is navigation in highly constrained spaces. So this is a comparison between a very normal, like a representative normal classical navigation environment classical approaches have addressed versus the highly constrained environments LFH is designed for. You can see the obstacles are so close to the obstacle that there's almost no actual clearance. So these places will cause a trouble for classical motion planners because they will need more computation. Sampling-based method will need more samples, and optimization-based method will need more iterations until convergence to find a feasible or optimal motion plan. And machine learning does not make things easier either, because for imitation learning, high-quality demonstration data is very difficult to acquire in those highly challenging spaces. And for reinforced learning, try and error is even more expensive because of the high probability of collision, because it's mostly will be error, not trial, right? So in LFH, so our observation is robots can comfortably perform a variety of very agile, very nimble maneuvers in relatively or even completely open spaces during previous deployments. Such maneuvers can also be optimal for certain highly constrained environments in the future. So I'm going to briefly talk about three different learning from hallucination methods, but let me first give you an overview idea using a graphical illustration. So during robot navigation deployment, you face a set of obstacles in front of you, and the job of the robot is to come up with a feasible or optimal motion plan to go through these obstacles without colliding and come to the goal. So the motivation of LFH is to squeeze every single bit of this existing navigation motion plan from previous deployment. So if I ask you this question, is the red motion plan also optimal for this obstacle? The answer is apparently yes. And how about this one? And how about this one? So it is very obvious that the red motion plan is optimal for all these different obstacle configurations, right? So therefore, we want a way to hallucinate, we call it, to come up with these obstacle configurations where this red motion plan is optimal. To be specific, we are going to talk about three different approaches. So the first hallucination approach is to hallucinate the most constrained, or we call it the maximum obstacle configuration, to make this red motion plan optimal. The second is to come up with a minimal obstacle configuration. And then in addition to this minimal set, we sample additional obstacles in addition to it. And the third one is learning in a self-supervised manner the distribution of obstacles where the red motion plan is optimal. And then we can sample in this learned distribution to come up with lots of obstacles to make the red motion plan optimal. So first, I want to give you some motion planning notations to get us on the same page. So we are dealing with the configuration space composed of the obstacle space and the free space, C obstacle and C free. Robot locates at the current configuration CC and wants to go to the go configuration CG. At each time step, the robot can take an action U, and a sequence of these actions will compose a motion plan P. A motion planner is basically a function F that maps from the obstacle configuration C obstacle to the optimal motion plan P, given CC and CG. And the motion planning problem is to find that function F to map from C obstacle to P. So in LFH, we propose to investigate the inverse problem of motion planning. So basically, given an optimal motion plan P, what is the appropriate obstacle configuration C obstacles to make P optimal? So our key observation here is, given limited onboard computation during deployment in highly constrained environment, it is very difficult for the F to find the optimal P. But if the inverse problem is much easier, given that P, we want to find all the obstacles, it can be done even offline after the field deployment. But unfortunately, you have seen in the last few slides, so one optimal motion plan has multiple different obstacle configurations. So this mapping is not well defined. What we really want is find a mapping from the optimal motion plan P to the set of all these obstacle configurations C obstacle I, where P is optimal. Apparently, this is an infinite set because there's an infinite number of obstacles where P is optimal. So we need to come up with ways to approximate this infinity set. The first way we propose is called learning from the most constrained hallucination. So for an obstacle set C obstacle to be the most constrained unreachable set, for C obstacle star, as we denote here. So for any obstacle set that will cause the optimal motion plan P, this obstacle set will belong to the most constrained unreachable set. So basically, the most constrained unreachable set is the set that contains all other sets where the optimal motion plan is P. So then we can train a function approximator, for example, using a neural network to map from the most constrained set to the optimal motion plan. This is pretty easy using a neural network. But the problem here is during training, the neural net has only seen the most constrained obstacle set, C obstacle star. But what if during field deployment, the robot faces not the most constrained set, but a realistic obstacle set as shown in the figure here? So this is where we seek help from a global planner from a classical navigation system. So using those sparse waypoints from a global plan, we can generate what we call runtime hallucination to hallucinate the robot during future deployment on the fly. So the robot can see the hallucinated obstacles and query our learned function and then come up with the feasible or even optimal motion plan. And to account for uncertainty, we also add perturbation to this motion plan and also adjust the speed correspondingly based on a forward rolling out model. So this is the most constrained case. So it works pretty well when, based on previous deployment in the future, when the robot still faces a highly constrained environment. But if the future deployment environment is not so constrained, it is relatively open, our learned motion planner may be too conservative because it is always generating those online hallucinations to hallucinate the robot on the fly. And the more important here is, what if a global path is not available to generate this runtime hallucination? So the most constrained hallucination may not work very well. So the inspiration of our second learning from minimal hallucination approach is, so not every single obstacle is required in that most constrained set to make such a plan optimal. So what we can do is we can just identify a minimal unreachable set instead of the maximum, and then randomly sample obstacles in addition to this minimal set, and then training our model, and then deploy without this so-called online runtime hallucination. So we call this hallucinated learning and sober deployment, or HLSD. So instead of the most constrained obstacle set C obstacle star, now we are seeking the minimal obstacle set C obstacle min. So for an obstacle set to be the minimal obstacle set, for any obstacle C that belongs to this minimal set, if we remove this obstacle from this minimal set, it will cause a different motion plan. So this is a little bit confusing, but let me give you an explanation using a point mass autonomic robot following the shortest path principle. So look at this graphical illustration. So the robot located at CC, current location, wants to go to the go configuration CG. So instead of a straight line, which is apparently should be the shortest path, why the robot take a detour through CM? So the detour through CM is probably because of some obstacle. So this is one example obstacle showing black here. So it starts at CM and ends at some point CE. Apparently, this straight line CMCE blocks the shortest path, the straight line path in the middle, but you also need to make sure there's no other shorter path than CCCMCG. So you want, on the other side, so the CCCCG is also shorter than the other side. So you want, this is basically asking the CE to be located on the ellipse, whose focal points are CC and CG. So CCCMCG on the right and CCCECG on the left will have the same length. That's the definition of an ellipse, right? So if you drop any of the obstacles along this line, such as this randomly chosen C, the robot will have a shorter path to go through that dropped obstacle C to come to CG, which is shorter than CCCMCG. So you cannot drop any of the obstacles along this CMCE line. Therefore, this little line is a minimal enrichable set. But unfortunately, there are many other minimal enrichable sets as well. These are just some examples. But fortunately, what we can prove in the paper, we have detailed proof in the paper. You can check it out if you are interested. What we can prove is, so the set of all these minimal enrichable sets, the set of them is living in this gray area, shown by a half ellipse and also a triangle on the right. So, and if we do, during future deployment, if the gray area is small enough, we can potentially just use one of them to represent all these black lines. For example, let's just use this representative one shown in figure D. So CM, CM prime. So CM prime is the symmetrical point of CM with respect to CCCG line. So this is the case for point mass holonomic robots. So that is one representative minimal obstacle set. So you cannot drop any of the obstacles along this line. So you may ask, how does it work for like a realistic robot with a real footprint from its own previous deployment experiences, like consecutive motion plans or trajectories collected from previous deployment? So in this slide, I will extend what the reasoning from the last slide to this realistic case. So we will use these little like red dotted lines to represent the polygons you have seen in the last slide. And those black lines are the minimal set, the representative minimal sets I talked about in the last slide. So these black spaces are where it must be obstacles. For other configuration in the space, such as on the top or on the bottom, so these places does not really matter. They can be free space or they can be obstacles, as long as there are no obstacles lie in the area swept by the robot footprint, delineated by the two blue boundaries. So other places don't really matter. So we just need to make sure those black lines are obstacles. Then we instantiate our our obstacle set using ray casting of laser range findings. For each of those laser beams, the blue boundary of the previous trajectory and the black minimal obstacle set, the little black lines, will determine the minimum value and the maximum value of each laser beam. So showing orange and yellow. So any value between this orange and the yellow value will still make sure the red motion plane is optimal. Then we can just sample many times between this minimum and maximum value and still assure the red motion plane is optimal. All these obstacles are good for this red motion plane. So very important here is we can account for uncertainty during data generation now. For example, if the red motion plane is moving very, very quickly, we know the robot is very confident. It is probably moving in very open space. So we can bias the sampling towards the maximum end to generate data. While if the red motion plane is moving very slowly, so we know the robot is being very conservative. It's probably moving in some realistic, highly constrained environment. So we bias the sampling towards the minimum end to generate data. So all these derivations, I really appreciate if you can follow me on all these, the maximum and the minimum and all the proofs and all the derivations. I know it's a lot of work and it's not easy to understand. If you get lost at some of the point, I don't blame you. But just motivated by that, we have developed our third called learning from learned hallucination methods. So in this, we don't need to manually prove or manually derive anything. No geometry, no nothing. The robot can actually learn a hallucination function out of itself, like in a self-supervised manner. So in LFLH, we use an encoder-decoder structure to reconstruct the motion plans. It's showing green here. The motion plans collected from previous deployments in relatively open or even completely open spaces. So our encoder-decoder structure is reconstructing those previous motion plans from previous deployment. And in our structure, the encoder is a learnable encoder approximated by a neural network, while the decoder, that's the key here. The decoder is a static, non-learnable, differentiable motion planner. So that's a classical motion planner there. So by using this as a classical motion planner, we are basically saying we are enforcing the latent space in the middle to be the distributions of obstacles where the green motion plan, the reconstructing plans are optimal. If we can learn that latent space in the middle is the distribution of obstacles, we can sample many times from this distribution and generate an unlimited amount of obstacles where the red motion plan is optimal. Then after generating all these obstacles, we also know the answers to these obstacles. That's the green motion plan. We can then train a learnable motion plan to map from the obstacles to the motion plan and can be deployed in the real world. So we have detailed proofs, also experiment in simulation in the Born dataset and also in the physical world in our papers. Feel free to check it out. But I just want to, for the sake of time, I just want to briefly give you an intuitive idea of how LFH works in the real world in naturally cluttered environments. So remember, the robot has never seen any of these environments before, but it learns how to navigate through these highly constrained environments by hallucinating on previous deployment experiences to generalize better into the future. Note how close the robot is to some of the frames, such as the one on the lower right. So those places will cause trouble for classical motion planners because they either need more samples or they need more iterations until convergence to find a feasible or optimal motion plan. But for LFH, it has learned that through training. So it can only need to query our constant neural net. So the computation is constant. It can navigate through without any problem. And if you think like designing these 2D hallucination for ground maneuvers is very difficult, so you must think it's probably impossible to design 3D hallucination for aerial navigation. So our third work, LFLH, because it's self-supervised, we don't need to design anything. There's no assumptions. There's no derivation. It can learn everything in a self-supervised manner. It can extend from 2D ground navigation to 3D aerial navigation in cluttered spaces and even for longer planning tasks. So this wraps up our third approach. LFH can allow robots to learn from their own self-supervised experiences from previous deployment to benefit the future, even like future more challenging or even adversarial deployments. So there's also some other navigation work going on in our lab. So for example, LFH addresses the problem. If we have successful previous deployments, we can also repeat the success again in future and arguably more challenging ones. But what if in previous deployments, some navigation experiences are unsuccessful? They may be getting stuck. There may be like collisions. Can we also utilize that? So this is a very recent work still under review right now. So it's called self-supervised environment synthesis. So in SES, we synthesize those difficult environments from past unsuccessful deployment experiences, and then synthesize those environments in simulation, so we can intensively train in those environments. Then in the future, if we encounter the similar difficult spots, they won't repeat the mistakes over and over. They will improve their performance. So in addition to like static navigation in static obstacle environments, we have also augmented our planners with social cues like gaze shown on the right to enable like a smoother or more interactive navigation among humans. So it's also worth to know that we have recently collected a very large-scale social navigation dataset. It's called a scanned and socially compliant navigation dataset. So it is composed of almost 10 hours, 25 miles, socially compliant demonstration of navigation behaviors in the wild, both indoor and outdoors, on 2 different types of robots. One is a wheeled robot, one is a legged robot, with 4 human experts collected in all these natural things on UT campus. So if we go back to this slide again at the very beginning, so machine learning can give our robots the ability to remove all these very strict assumptions of currently deployable robots. And of course, we have been only covering navigation today, and there's other more important tasks to be addressed using learning as well, which we will do in the future. So with more and more robots being deployed in the field, so not only one single type of robots will be deployed, but many different types, such as wheeled, tracked, or even legged, and by different types of human users, not only one type of user. So I envision the future robots deployment will just simply work out of the box, and what the human users need to do is simply press a button and walk away. First of all, this will require a single robot in that fleet to continually improve across multiple deployments. So we have a very recent work show on the right there. So it's called lifelong learning for navigation. It addresses the problem. So it's used a lifelong learning technique to adapt to future navigation environments. But when you come back to the previous deployment environment, you don't incur this so-called catastrophic forgetting in machine learning. In addition to single robot like continuing improvements, we also want the entire robot fleet to have collective improvements among the whole fleet. So for example, like a wheeled robot need to learn from other wheeled robots, also maybe other tracked robots, or even other legged robots as the spots on the right. So the reference on the right is our recent work called VOLA, visual only imitation learning from observation. So it's also tackles navigation. So a wheeled robot can actually learn from navigation experiences from a legged robot, even if they have completely different motion morphologies. That's the work we have done in the past. So also, this whole human-robot community together with robots, with humans, they also provide us with a very rich source of information we can utilize to improve the entire robot's fleet's performance in the future. One interesting direction we should investigate in the future is, so how to balance the trade-off with human users, like firefighters, like responders, like agency stakeholders, like the elderly, like all the different kind of users. How do we balance the trade-off between them? Because they have different priorities, different like preference, also different skill sets. How can we utilize all this knowledge from those non-expert users? So in conclusion, with our research goal of developing highly capable and intelligent mobile robots that are robustly deployable in the real world with minimal human supervision. So we adopt a field methodology to identify real-world deployment problems, because that's where the problems are. And our expertise is evenly grounded in both classical motion planning to create capable mobile robots to be deployable in the real world, and also machine learning to equip those robots with intelligence and to enable orthogonal capabilities. So our future research agenda is to build a hardened, reliable, and also resilient robot fleet, which is not only good at navigation, but also being very task efficient at other tasks and continue to learn from each other and also from humans. So I believe this will be the key to get us closer to the ideally deployable robots I showed in the first few slides, such as deploying not only one single Iron Man, but the entire Iron Legion to autonomously and also efficiently save our lives during any disaster responses. So with this, I would like to thank my own Iron Legion, my collaborators from the Learning Agent Research Group at UT Austin, from the Center for Robot Assisted Search and Rescue at Texas A&M, and from the Biorobotics Lab at CMU, who all contributed to creating these deployable robots covered in this talk. So with this, I conclude my talk, and I'm happy to take any questions.
Thanks a lot. This is a very, very cool talk. Questions from the audience? Let me get the questions rolling. So the for the first part, but I think in general, okay, let's focus on the first part, right? When we talk about non-experts, what's special about non-experts? Like, what's the differentiation between non-experts versus experts? What specific challenges do you have to deal with when you're talking about like getting feedback from non-experts? As opposed to getting it from experts.
Yeah, so I guess hold that thought for a while. So first of all, a non-expert and expert, what we define as roboticists who know how the internal system works. Like he knows move base, he knows what parameters are for what functionality. So that's expert. So they don't need to use our Apple method at all. They can just go in there, fine-tune the system, come up with the best set of parameters, and then deploy. But we don't have that luxury. Like firefighters do not know how to tune the system. Like first responders just know how to bring the robot to the field, right? So that's what we distinguish between expert and non-expert. And within experts, within non-expert, there's also different like skill sets. Some people are more versed with robotics, so they may be gamers, they know how to use a joystick. So that's where we can ask them to, hey, give you a joystick. Can you just drive the robot, show what's the desired navigation behavior looks like? They probably can do that. Right? So there's also some users who are not familiar with these things at all, but they probably know like if the robot gets stuck there, that's not a good thing, right? They should go through. If the robot collides, that's also a bad thing. What they can provide is evaluative feedback. This is a good job, this is a bad job, or this is a very good job, or this is a very bad job. So depending on the skill set, we can like discretize or maybe even give a continuous range of different like evaluative feedback. Then these users can also contribute to improving the system performance during field deployment.
So do you have to deal with forgetting expert feedback? So if non-expert feedback, I suppose. So what if a non-expert self gives suboptimal or incorrect evaluations or demonstrations?
Yes. So that's actually the motivation of our Apple I work, the second one. So we started with Apple D. You give a full teleoperated demonstration to show the whole desired trajectory, how it looks like. The problem is humans are suboptimal at some point. And at some point, the default system parameters are already performing pretty well. That's where we use Apple I. So if you cannot do a good job, don't do it. Only do it when you think the robot is failing. Then you intervene. That's what we call Apple I from interventions. You only intervene at this specific location. For other places, like let the robot do its own thing. Like we use, to be specific, we use a confidence measure in the context predictor. So it will identify this is probably the context A where that human user intervened. Let me use that parameter I learned. But this is probably A, probably B. I'm not very confident. That's probably not, I should not use anything learned. I should just go back to my default parameters. That's how we cover these like imperfect demonstrations. Yeah.
Awesome. Thank you.
Yeah.
Questions from the audience?
Hi, thank you for your presentation. It was really nice. I really enjoyed the last part of your talk. I think it's a very interesting idea what you did there. I was wondering for your last part of your talk, can you discuss a little bit about the scalability of learning? Do you perform any offline training to kind of generalize those trajectories to various obstacles environments?
You mean, so the learning from hallucination work?
Yes.
So the idea of that is to generate as many like plausible obstacles as possible where the existing experience is already optimal, right? So all these are offline. We don't do that online.
Okay.
So yeah, we have previous deployment is a small set of like motion trajectories. We just want to tap every single bit out of this existing like pool of knowledge by generating. So we have the answers already. We have one question we asked in the past, which we have one answer, right? We want to come up with all the questions where this answer is still correct.
Yeah.
So hopefully we can generate all of them, but apparently it's not possible. That's why we need to approach this impossible problem with approximation. That's the 3 approach I talked about. To come up with questions, come up with obstacles where the existing previous motion plans are already optimal.
Yeah. So essentially you have an extensive offline training where you create a library and then you deploy the robot and according to what the robot sees, finds the corresponding library item and follows that path, I guess.
Yeah, you can. In some sense, it is like that, but it's not really like an explicit lookup in the library. So we use that as a neural net, right? Yeah. The neural net learns on all these scenarios, and then it can generalize during future deployment. Yeah, I guess you can do a lookup, but you need a very efficient way to do that, right? Because you are generating lots of different obstacles during your training, and you cannot memorize all of them, and you cannot even look it up very quickly during deployment. Yeah, so that's why we use a neural net, because what we know about neural net is the querying time is constant. And if we can have a decent capacity of the neural net, and we have seen lots of good training samples, it can generalize well into the future.
I see. Yeah. All right. Okay. Thank you.
I have a question about the. I think was it Apple that you showed with the car and the obstacle.
There's multiple cars in the obstacles, like off-road or not off-road.
Where it seems like a backyard going from this.
Yeah, backyard is the LIKD work. Yeah, okay. Learning Inverse Kinodynamics.
Okay, so how does that work in a dynamic environment, right? Where your environment, not necessarily that you have people moving around, but more so the terrain that you're on is dynamic. So maybe your robot is driving on mud or is driving in a stream or something like that. How does that work?
Right now, we actually don't have anything to specifically deal with that. But I guess the beauty of this LIKD work is it learns not from a curated data set. It is learning like online learning sort of deal, right? So you feel the environment while you're exploring, when you're deploying, and then based on those feedback, you learn to update your model. So even if your environment is changed, so we don't map anything, so nothing is static. It is static, obstacles are static, and the terrains are static, but we don't map anything. We don't know, okay, here is going to be grass, here is going to be terrain. We only sense what it is when we are on it, and then respond correspondingly. Yeah, I guess the short answer is we don't have a good way to deal with dynamics right now, but I think it has some potential already to cover these changing terrain types.
So in environments where potential sensing is continuously changing, like for example a USV on a stormy ocean, exactly how would the system constructed adjust to that? Since it's not it's not just the obstacles that might be changing, but the very navigation environment itself at any time step.
Yeah, so that is what I talked to Troy about it. So you sense the environment through your own vehicle terrain or robot environment to be general robot environment interactions. And then using that data, you try to update your model. And then the updated model can cover these changes. Right? For example, if you have some new terrain coming up you have never seen, right? You drive over it, you see, okay, there's a discrepancy between my believed model versus what I'm actually observing. Then you can update your believed model to adapt to those scenarios.
Yeah, I have a question about your Apple work, especially for that Apple RL. So I guess, is that to my understanding, so the Apple work is basically a parameter learning. You learn a parameter policy and then you feed it into an existing planner, which is a local planner in some sense. And the problem is that for that Apple RL1, is that your local planner is a differentiable planner?
No, it's not. So it's called DWA planner, dynamic window approach. Yeah, it's a pretty old planner. So it's not differentiable. It's sampling based.
So then it's not end-to-end then?
No, it's not. So for the Apple R, like the graph I showed, like the meta environment. So the environment is not only the physical with W, but also the DWA planner. That's the motion planner G. So that's our environment. Then the MDP is constructed on top of that. Yeah, so it doesn't need to be differentiable, but of course, if you have a differentiable planner, there's lots of benefits. You can even make the training faster. Right now, for example, Apple D takes a while to train because it's a black box optimization. Right, so basically you need to try different parameters to see where the local minimum is. If if your planner is differentiable, there's other things you can do to make it much faster.
Okay, yeah. So my second question is about, so for the Apple work is very interesting. So you basically improve is actually lifelong pattern. So basically you just like learning on the way and then you keep improving the navigation. But this work, I think to my understanding, is more focused on the local planning.
Yes.
Basically Chinese action or try to optimize your local trajectory.
Yeah.
Are there any ongoing or some other works on the global planning such that you pick the waypoints better, not just like to generate action better?
I think we do not have ongoing work on this, but I think that's definitely possible. So basically, you can use the same setup. So the output of the global planner is a set of waypoints or a global plan, right? You can also demonstrate your desired global plan, and then you use the same Apple paradigm on top of it, and then try to tune the parameters of a global planner to come up with very similar global plans, right? But there's one caveat here is because we pick local planner for a reason, because there's a limitation of what you can learn, because no matter how much you have varied the global plan or even the local plan parameters, there's some actions it will never produce. So that is challenging because if you want the robot to go around, like make a detour because something in the middle, maybe the global planner will never give you that, like with every different combination of parameters. So the more flexibility in the planner, in the global planner, that's actually the reason why we did not choose to do the global planner. For the local planner, it's more, I would say, it's more constrained. There's only a small room, a small space the output can be. Then by tuning the parameters, you can reach every single point in the space, not anywhere else. That is one caveat. So we haven't tried that yet, but we think that will be a problem if you deal with global planning.
Yeah. So one last question. So for the application scenario, I'm very interested in your work in one application scenario, whether it works. So if you do a long range navigation and it's recurrent, not one single episode, that's just for your application scenario. But the environment is dynamic. Some of the obstacles may be gone, there may be actually some other obstacles appearing. Will that keep improving as long as you keep doing the...
So so in the cycle of learning scheme, that's the goal of it. So we also need humans in the loop. So if you have some new dynamic obstacle popping up, then you may have suboptimal behavior, like facing that obstacle, facing that new thing, right? If we have non-expert users in the loop, maybe like someone who just walked by, he or she can choose to intervene or to give either feedback or to demonstrate, to choose the appropriate interaction modalities, as we call it, to tell the robot, hey, you should improve now. This is not good. Then it will have the potential to keep improving. That's why we have the cycle. So it's always through, the cycle does not need to be following that order, like Apple D, Apple I, Apple E, and Apple R. It could be in any order, depending on the user's preference.
Yeah, well, thank you.
So in the medical robotics scene, a lot of the motions that are made by the robot are trained by the surgeons that are kind of operating it. But the thing is that some of the operations like suturing, this was at a recent talk that I went to, inside the body might vary by body type and tissue type and whatnot when actually doing it. So I was kind of curious as to how the system would perform in such cases where you have to have a large majority in the grand case for how the medical robot would work on the body, be trained by scientists teleoperating it. But then when it comes to the local levels, might have to do different operations when working with smaller cellular parts.
So I think the general principle should be very similar, but right now we don't do that autonomously because that's pretty critical. That's like medical applications, right? I would say all these teleoperation experiences like from the data from the expert surgeons, all these professionally trained personnel, these data will be very helpful to at least open up something for autonomy. Maybe not the full, like we don't want autonomous surgery. That's probably too scary right now. But there could be things that these data can help so that it can assist humans to make like fewer mistakes, to be like less burdensome, to be more easy to operate, I would say. Yeah.
Right. So
what time? Oh, we have past
I think we can stop here, but there's looks like there are more questions, so we can just hang out and answer more questions. But thanks a lot for an excellent talk. Clearly generated a lot of interest. And I know there's a bunch of people watching online as well, so you might get questions down the line. But thank you for visiting us.
No problem.